if that moose came to live in your house? Would you read him a book? Would you teach him to cook? Would you ask him to dance? Would you dress him in paint? Oh, hi there. Decided to join us for story time, did you? Just kidding. Let's do some math here, of course. Got some letters here that we can spell with. Let's start with the word father. So one question that you should be comfortable with by now is, how many permutations are there for the letters in the word father? So how many different arrangements are there? You know, we can mix those letters up however we want. Well, the answer, of course, is there are 1, 2, 3, 4, 5, 6 letters. So there are 6 factorial, or 720 different arrangements of the word father. Let's move on to a bit of a more interesting example. How about if we look at the number of permutations of the letters in the word school? This is significantly different. At first, you count the letters, and again, there's 6 letters. But the answer is not 6 factorial. Can you see why? It has to do with the double O's. Now here, my double O's, it's kind of nice that they're a different color, but we're going to assume that we're talking about the letters in the word school, and we're not going to distinguish between the 2 O's. So here's one arrangement. That is not a different arrangement, however. Here is another arrangement, but this is not a different arrangement. So if at first we were to say that the answer is 6 factorial, we have actually counted too many permutations, because like I said, this is no different than this. So if you think about it, how many 720, how many too many is that? Well, it's exactly twice as many as there really are, because for every combination you come up with, you've counted a different combination where you switch the O's. So actually the answer is 6 factorial divided by 2, or 720 divided by 2. There are 360 different arrangements in the letters of the word school. Now I'd like you to notice something about this calculation. This is going to be important later on. The number 2 happens to be the same as 2 factorial, since 2 factorial is just 2 times 1. So I could also say 2 factorial. That's going to bring us to our next example. How about the word masses, where we're saying, again, we have 1, 2, 3, 4, 5, 6 letters. So we might be tempted to say there are 6 factorial arrangements, but there are not, because many of these arrangements are the same. For example, 6 factorial, if that's our answer, that means that we're assuming that switching these 2 S's results in a different word when it doesn't. Or that here is one permutation, and I might be tempted in that 6 factorial, that's 720 by the way, I would be saying that this is different than this, which it isn't. In fact, this is also another permutation that's counted that shouldn't, and here's yet another permutation that's counted but shouldn't be. So the question is, what about these S's? There are 3 of them, and they are the same letter. So for every permutation you come up with, you can then start thinking about how many ways can I arrange the S's? Well, I can arrange the S's in 3 factorial different ways, which is 3 times 2 times 1, which is 6. So for all of those 720 different arrangements, I've overcounted 6 times the number that there really are, because there are 6 different ways of just arranging the S's. So really our answer is 6 factorial divided by 3 factorial, which is the same as 720 divided by 6. Let's take a look at some more examples together. So there's the answer to the first question about permutations of the word father, including if you were to only use 4 letters instead of all 6. And of course, our answer for school and for masses, which are different questions because of the repeating letters. And let's try another one. How about the number of permutations of the word Roshire? Well, notice that in this case, the first thing you hopefully notice is that there are, if you count them up, there are 9 symbols. So at first we might be tempted to say it's 9 factorial ways of arranging those different letters. However, if we did it that way, we would be counting a lot of different permutations that are really the same. For example, there are 3 S's there. So even if we just took the word Roshire, we could start switching these S's around, and we would get those have been counted as different permutations even though they're really the same. Well, there are 3 factorial ways of rearranging those S's. There are also, if you notice, 2 R's as well. So even though after we took 9 factorial and divided 3 factorial out, we would still be counting twice as many permutations as there actually is because of the different ways you can arrange the 2 R's, or 2 factorial ways of arranging the R's. So in this solution, the 3 factorial, because there's 3 S's, and the 2 factorials for the 2 R's. Now if you take 9 factorial divided by 3 factorial and divided by 2 factorial, you get 30,240 permutations. Now in general, we can say that the number of permutations with identical objects can be always done this way. So the number of permutations is n factorial, okay, if there's n objects, divided by if there are A identical objects of one kind, B identical objects of another kind, C identical object of a third kind, and so on. That's what that looks like. That's meant to be let me just clean that up a bit, sort of a dot, dot, dot there. For example, consider bookkeeper. There are 10 characters here, 10 letters in bookkeeper. However, there are a lot of the letters that are the same. Let's look at the O's, for example. There are 2 O's. There are also 2 K's, bookkeeper, and there are also 3 E's. So we must divide by those numbers to take into account all the different arrangements of the O's and the E's and the K's. If you figure that out, you get 151,200. In this next example, let's make things a little bit more interesting. Imagine all the 3 E's must be side by side in our permutation. And I've given you one example of that, where I have my 3 E's here all together. Now how many possible arrangements are there? I hope you realize that number has to be less than 151,200. As soon as we start adding restrictions, we lower the number of possibilities. There's a trick to doing this one. What I'm actually going to do is I'm going to pretend the 3 E's are one letter, in which case I now have 1, 2, 3, 4, 5, 6, 7, 8 different letters altogether, treating the E's as one. There are 8 factorial ways of rearranging this, and that means the E's are stuck together. However, I still got to be careful. There are still double O's and double K's, so we don't want to double count those. If you figure that out, sure enough, you get a number much smaller than 151,000, a little bit bigger than 10,000. How about another example where we decide that the B and the R must be side by side? And I've given you one example where that's true, right here. Well, the strategy is very similar. We treat the B and the R as if they're one letter. And now there are 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. So 9 factorial ways to arrange those. However, divide by, we have triple E's, double O's, double K's. However, excuse me, side by side, I'm not sure if, well, I wrote this question, but does it count, like, can the R come first and then the B? If so, there's more possibilities, because I could actually say that this is okay as long as R and B are still side by side. So that actually doubles all the answers. Or multiply by 2 factorial, which is the same as 2, all the different ways you can arrange a B and an R. If you do that and figure out what that is, you should get 30,240. Now, many different questions can be solved in probability using the ideas behind permutations. Take, for example, the soccer team that we know in 20 games had 16 wins, 3 losses, and 1 tie. And we want to think about the order that these events could happen in which case we can actually say that the soccer team's 20 games can just be represented by a string of characters. For example, W, W, T, L, L, W, W, and so on. I mean, that has to be 20 long. I'm not going to write it all out. Might be one possible win, tie, loss scenario. And as long as, I mean, okay, so a win against Hanover might be different than a win against Sacred Heart, but as far as the order in which these things could happen, we could say that they're the same, that this completely describes their 20-game season. Okay, well, there are 20 characters. There are 20 ways to rearrange the W's, L's, and T's. However, there are lots of repeats. There are 16 wins, and there are 3 losses, and there's 1 tie. Notice we can even divide by 1 factorial if we want, but we certainly don't need to. That gives you 19,380, the number of orders, wins, losses, and ties could happen for the soccer team. Now we could move on to this next question, which is a little bit more difficult. Assuming the order is completely random, okay, what is the probability that the team lost 3 games in a row? Well, now you're basically saying we're only interested in outcomes where the 3 losses appear together. Okay, so just like before, we can treat the 3 losses as if they're now 1 character instead of 3. And so instead of having 20 games, it's like we have 18 games, where 16 of those symbols are all wins. And so we divide by 16 factorial. This is me here basically coming up with the number of ways I can write the 20 games out where the 3 losses always appear together. I could also divide by 1 factorial for the tie here, but I don't need to do that. Now this is a probability question, which means we're saying that's the number of ways that I can expect to see outcomes that look like this, with the 3 losses together, divided by our total number of outcomes. If you figure that out, I believe you get about 1.6%. It's actually shocking how much smaller this is than 19,380. Now, is this a reasonable assumption? And that assumption, I mean that the order is completely random? I would say no, not in real life. In real life, it's quite likely the losses are grouped together. They're not likely independent events. If you lost 1 game, probably your probability of losing the next went up because, I don't know, maybe your best player is hurt, or maybe you're just having a bad streak, or you're having a good streak. So it's not a fair assumption. We would never assume that wins and losses and ties are dropped in random order over a season, but I guess it could be true. Another similar example would be coin flips. A coin is tossed 8 times. Find the probability of getting, well, let's think about coin flips as also being just a string of letters. Here's one example. Head, head, head. Tail, 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 tail. So there are, another example might be head, tail, 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 head, head, head. I think that's 8. 3, 4, 5, 6. Yep. So there's all sorts of possibilities. Well, how many total outcomes are there when you toss a coin 8 times? Well, our total outcomes would be something like 8 factorial I'm just going to pause this for 1 second. Okay, sorry about that. Let me back up just a bit. the first example here was good that I wrote down. The second one, not so great. Okay, here's one way to have 3 heads and 5 tails, 3 H's and 5 T's. Another way might be, you know, tails, head, another head. That's what, 1, 2, and then 3 tails. Okay, there's 5 tails and 3 heads there. Well, how many possible outcomes are there from tossing a coin 8 times? Well, considering all the examples, there are 2 to the 8, or 256 outcomes. Because basically what you're saying is, look, there are 8 spaces for each flip, and each of them has 2 choices. You can be an H or a T. So 2 times 2 times 2, 8 times gives you 2 to the power of 8, 256 outcomes. Now, how many of those outcomes have exactly 3 heads and 5 tails? Is how many of these can I create? Well, there's 8 spaces. I need 3 of them to be heads and 5 of them to be tails. So it's really, how many ways can I write 3 heads and 5 tails? How many ways can I arrange this word, which has 8 letters, however 3 of them are H's and 5 of them are T's? That answer is 56. And then our probability for our answer will now be 56 divided by the total number of 256. And if you figure that out as a percent, I believe you get about 21.9%. Exactly 4 heads and 4 tails? Well, now you're talking about something like head, head, tail, 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 tail. Head. There's one possibility. How many outcomes are there that look like this? Well, 8 different letters rearranged. However, 4 of them are identical and 4 of them are identical. That gives you 70 possibilities if you figure that out. And so the probability of that happening is 70 divided by 256, which is about 27.3% is what I have here. So we can see that permutations can be used to solve real-life questions as well. In fact, this question without permutations is quite difficult. For this example, assume we have 12 basketball players lining up for a photograph. How many possible arrangements are there if? Well, let's just start with, is no if. 12 factorial is how many ways that 12 people could be rearranged in line. That's a huge number. Let's just see how big it is. 12 factorial. There you go. 479 million. How about if there's 3 captains and they must stand side by side? Well, this is kind of like our other example. Imagine we have these 12 spaces. But 3 people must be side by side. So I can imagine taking the 12 people and grouping those 3 players together. Well, now there's 10 players. 1, 2, 3, 4, 5, 6, 7, 8, 9, plus the 3 captains, which we're now treating as 1 person. So you have 10 factorial ways of arranging the 10 people. However, the 3 captains, for each of those arrangements, you could then rearrange the captains, and they can be rearranged 3 factorial ways. You get something that's like a little bit bigger than 21 million, almost 22 million when you do that. For our last example, assume that there are 2 players, Jeb and Ryan, and they do not want to stand beside each other. That's kind of a difficult question. So just like with some other probability examples, my suggestion is that you think about the complement. Think about the opposite case. In this case, it's easier to think about them standing together. If we assume that they must stand side by side, they become 1 player now, and there are 10 other players, so 11 players in total, can be rearranged 11 factorial ways, times 2 factorial, because there are 2 ways to rearrange Jeb and Ryan. So that's assuming this is 79,833,600 ways that Jeb and Ryan can stand together. Well, we actually want them to not stand together, so we subtract that from the total. And we get an answer of, it's gigantic again, 399,168,000 different ways of arranging 12 players on a basketball team where Jeb and Ryan don't stand beside each other. Okay, good luck with the questions I've assigned. Please, again, send me an email if you have any trouble. Bye for now.